Hi everyone. Today we're going to study Pythagorean theorem. First, let us define right triangle. A right triangle is a triangle with a right angle. We know that right angle means it is a 90-degree angle. Here's a picture of a right triangle. The small square on that corner denotes a right angle. Consequently, this triangle is a right triangle. Let us label the sides. This side here is called the hypotenuse. Conventionally, it is named as side C. This hypotenuse is the side opposite this right angle, and we say that the hypotenuse is the longest side of a right triangle. For the two other sides, we can put letters A and B interchangeably. In here, I put in this side to be A and the base to be side B. Let us go now to Pythagorean theorem. Given the right triangle, the formula for the Pythagorean theorem is c square equals a square plus b square. In words, in a right triangle, the square of the length of hypotenuse is equal to the sum of the squares of the two other sides. Let us have example 1. Find the missing side of the right triangle below. The two sides are given. We can see here that the missing side is the side C, which is the hypotenuse. We will use the Pythagorean theorem to solve the problem. C square equals a square plus b square. We will do the substitution now. C square equals the a square now becomes 3 square. Then plus the b square is now 4 square. Then we will simplify further. The 3 square is 9 plus 4 square is 16. We will just copy the c square down here. Then we will add this 9 and 16 becomes 25. We want the value of c, so we're going to take the square root of both sides. So this is now square root of c square equals the square root of 25. We can now cancel the radical and the square. Only c comes down, and the square root of 25 is 5. So this 5 value is the required side. This is our final answer. Let us have example 2. Find the length of the missing side of the right triangle below. In the figure, the missing side is the base, and this is denoted by A in this problem. The hypotenuse is 12, and the side here is 4 units. Our Pythagorean theorem is here that we're going to use to solve the missing side. Substituting now the values, the c square is now 12 square, that is the hypotenuse to be squared, equals the a square, that is the missing side, plus the b square is now 4 square. Then we will simplify further. 12 square is 144 equals a square plus 4 square is 16. We want this a square to be isolated. The positive 16 we will transpose on the left side. We will not forget that the sign must be changed. So the positive 16 becomes negative 16 on the left side. So here now is 144 minus 16 equals a square. Simplifying this, we have 128 equals a square. We will take the square root of both sides. We'll have now square root of 128 equals the square root of a square. So we can cancel the radical and the square. Only a comes down here. For the square root of 128, we will simplify this further by factoring out the 128. One factor must be a perfect square. So this is 2 times 64. We know that the 64 is a perfect square number, and the square root of 64 is 8. So that value 8 will go out of the radical sign. Just to put this a on the left side, we can interchange this right hand and left hand side. So a is now on the left. This is equal to the simplified square root of 64 is now 8 times the square root of 2. Only that 2 remains as radicand. So this a, 8 square root of 2, is the required side. This is our final answer. Hi everyone. Today we're going to study direct trigonometric functions or ratios. We have here a right triangle. First, let us label the parts of the right triangle. We can see here the small square that denotes right angle, and the side opposite is what we call the hypotenuse. Then, for the two angles here, let us name one angle to be theta, and the side here is the opposite side of theta. And the last side will be called the adjacent side of the angle theta. We will now specify direct trigonometric functions. We will begin with the sine theta. The symbol for sine is sin theta, and this is equal to the ratio of the opposite side over the hypotenuse. The next function is cosine theta. The symbol is cos, and this is the ratio of adjacent over the hypotenuse. The next function is tangent theta, and the symbol is tan. This is the ratio of the opposite side over the adjacent side. There is a popular mnemonic to help us remember quickly the three functions here. This is the SO, KA, TOA. The SOH is for the sine. The S here is the first letter of the sine. The O is for the opposite, and the H is the hypotenuse. The Ka is for the cosine, with that first letter C to denote cosine. The A is adjacent, and H is the hypotenuse. TOA is for tangent, where T is the first letter of the tangent, the O is the opposite, and A is for the adjacent side. So TOA. We'll go now to reciprocal functions. Let's begin with secant theta with a symbol SEC, and this is the ratio of hypotenuse over the adjacent side. This is called reciprocal function because this is the reciprocal of cosine. The next function is cosecant theta. with a symbol CSC, and the ratio is hypotenuse over opposite side. This is the reciprocal of the sine. The next function is the cotangent theta, symbolized by COT, and this is equal to the ratio of adjacent over opposite side. This is the reciprocal of the tangent. Let us have example 1. Using the triangle shown below, evaluate sine alpha, cosine alpha, tangent alpha, secant alpha, cosecant alpha, and cotangent alpha. In this triangle, the angle alpha is here. So the opposite side is here with the length 4. This is our right angle, and opposite to that is the hypotenuse with length 5. And the side here is the adjacent side with length 3. Let us now start evaluating the ratios. Let's begin with the sine alpha. The ratio is opposite over hypotenuse. The opposite is 4 and the hypotenuse is 5. So this is 4 over 5. Next is cosine alpha. The ratio is adjacent over hypotenuse. The adjacent side is 3 over the hypotenuse, which is 5. So cosine alpha is 3 over 5. Next is tangent alpha, and the ratio is opposite over adjacent. The opposite is 4 over the adjacent, which is 3. So tangent alpha is 4 over 3. Next is secant alpha. The ratio is hypotenuse over adjacent. Hypotenuse is 5 over the adjacent, and that is 3. So secant alpha is 5 over 3. Next is cosecant alpha. The ratio is hypotenuse over opposite. Hypotenuse is 5 over the opposite, which is 4. So cosecant alpha is 5 over 4. Last is cotangent alpha. The ratio is adjacent over opposite. Adjacent is 3 over the opposite, which is 4. So the cotangent alpha is 3 over 4. So we are now complete with our ratios. Let us have example 2. Given the triangle shown in the figure, find the values of all trigonometric ratios or functions of the angle alpha. The angle alpha is here. We have the length of two sides, 15 and 8. The length of one side is missing. That side is the opposite of the right angle, and that is the hypotenuse. So first, we will calculate for the hypotenuse. We will use the Pythagorean theorem. We will assign letter C to the side which is the hypotenuse, and the formula will be c squared equals a squared plus b squared. Substituting now the values, we have the c squared equals 15 squared plus the 8 squared. Simplifying further, the 15 squared is 225 plus 8 squared is 64. Then we will add the two numbers, it becomes 289. So c squared equals 289. we will get the square root of both sides. Only c will come down here, and we will take the square root of 289, which is equal to 17. So the value c is 17. Then we will start writing our trigonometric ratios. Let's begin with the sine alpha. We know the ratio is opposite over hypotenuse, and that is equal to 8 over 17. The next is the cosine alpha. The ratio is adjacent over hypotenuse. The adjacent is 15 over the hypotenuse 17. So cosine alpha is 15 over 17. The next is the tangent alpha. The ratio is opposite over adjacent. The opposite side is 8 over the adjacent, which is 15. So tangent alpha equals 8 over 15. The next is secant alpha, and the ratio hypotenuse over adjacent. The hypotenuse is 17 and the adjacent is 15. So secant alpha equals 17 over 15. Next is cosecant alpha, and the ratio is hypotenuse over opposite. The hypotenuse is 17 over opposite, which is 8. So cosecant alpha is 17 over 8. Last is cotangent alpha, and the ratio is adjacent over opposite. The adjacent side is 15 over opposite, which is 8. So cotangent alpha is 15 over 8. We have now written all the trigonometric ratios, and this is now the final answer. Hi everyone. Today we're going to study fundamental trigonometric identities. First, let us define trigonometric identities. In mathematics, trigonometric identities are equalities that involve trigonometric functions and are true for every value of the occurring variables for which both sides of the equality are defined. In this video, we are going to consider 4 types of identities. Number 1, Pythagorean identities. Second, even-odd identities. Number 3, reciprocal identities. And number 4, quotient identities. Let's begin with Pythagorean identities. The first identity for this group is sine square theta plus cosine square theta equals 1. Second, 1 plus cotangent square theta equals cosecant square theta. Third, 1 plus tangent square theta equals secant square theta. The even-odd identities relate the value of a trigonometric function at a given angle to the value of the function at the opposite angle. The first identity is the cosine of negative theta is equal to cosine theta. Second, the secant of negative theta equals secant theta. Third, the sine of negative theta equals negative sine theta. The fourth, cosecant negative theta equals negative cosecant theta. Fifth, tangent of negative theta equals negative tangent theta. And the last, cotangent of negative theta equals negative cotangent theta. For the reciprocal identities, the first identity is sine theta equals 1 over cosecant theta. Second, cosine theta equals 1 over secant theta. Third, tangent theta equals 1 over cotangent theta. The fourth, cosecant theta equals 1 over sine theta. Fifth, secant theta equals 1 over cosine theta. And the last, cotangent theta equals 1 over tangent theta. The last group is quotient identities. Tangent theta equals sine theta over cosine theta. Second is cotangent theta equals cosine theta over sine theta. We are going to simplify trigonometric equations using identities, and here are the general points. Number 1, simplify both sides of the equation using appropriate identities. Number 2, preferably convert all functions into sine or cosine functions and apply algebraic simplifications. Let us have example 1. Verify tangent theta cosine theta equals sine theta. We can see in this problem that the right hand side is already simple, so we are going to simplify the left hand side to make it equal to the right hand side. I will copy the left hand side member. Again, this is tangent theta cosine theta. I am going to convert all functions into sine or cosine. So the tangent theta here, I will convert into sine or cosine function. The second, the cosine theta is already a cosine, so I will leave it as it is. Using the quotient identity, I know that tangent theta equals sine theta over cosine theta. I am going to use this value to replace the tangent theta here. So the left hand side becomes sine theta over cosine theta, replacing the tangent theta, times the cosine theta I simply copied. And from here, I can see that the cosine theta can be cancelled with the denominator, which is cosine theta also. After the cancellation, only the sine theta will remain. And we can see here that the left hand side is now equal to the right hand side. And we are able to prove that the left hand side is equal to the right hand side. Let us have example 2. Verify the following equivalency using the even-odd identities. The quantity 1 plus sine x times the quantity 1 plus sine of negative x equals cosine square x. In this problem, we can see that the right hand side is already simple, and the left hand side is a little bit complex. So we will simplify the left hand side to equal that right hand side. I will copy again the left hand side here. There is a term here, the sign negative x, to be simplified using the even-odd identities. From the odd identity, we have this sign of negative theta equals negative sine theta. Using this idea, I will now simplify this sign negative x. It is now replaced by negative sine x. And to simplify the plus and the minus, I will simply write minus. So the new left-hand side is 1 plus sine x times 1 minus sine x. In algebra, if we multiply sum of two terms times the difference of two terms, the product will be the square of the first term minus the square of the second term. So multiplying the 1 plus sine x times 1 minus sine x, I have here now 1 minus sine square x. From the Pythagorean identity, we have this sine square x plus cosine square x equals 1. Doing some manipulation on this formula, I will transpose the sine square x on the other side of the equation. The sign will change, so I have now cosine square x equals 1 minus sine square x. This 1 minus sine square x is the same value that I have in the left hand side, so I can replace this value by the cosine square x. So here it is now. And the cosine square x, I can see that this is now equal to the right hand side. So we are able to show that the left hand side is equal to the right hand side. Let us have example 3. Verify the identity, the fraction, with numerator secant square theta minus 1 all over secant square theta equals sine square theta. In this problem, the right hand side is simple, the left hand side is a fraction, so we will simplify the left hand side to equal the right hand side. I copied the left hand side in here, and then one Pythagorean identity says secant square theta equals tangent square theta plus 1. I am going to replace the secant square theta of the numerator with this value tangent square theta plus 1. So I have here now tangent square theta plus 1 minus 1 all over the secant square theta. If I remove the grouping symbol here, the plus 1 and the minus 1 will cancel each other. So after cancellation, I will now have this tangent square theta over secant square theta. I'm going to split now the tangent square theta and the secant square theta, showing that this secant square theta is a fraction with numerator of 1. And then I am going to convert the functions into sine or cosine. The tangent square theta, I can use the quotient identity. It is equal to sine square theta over cosine square theta. While the 1 over secant square theta, I can use the reciprocal identity to show that this value is equal to the cosine square theta. Substituting now the respective values, the tangent square theta is now replaced by sine square theta over cosine square theta. while the 1 over secant square theta is equal to the cosine square theta. From here, I can see that this cosine square theta can be cancelled with the cosine square theta in the denominator. After the cancellation, only the sine square theta remains. And from here, I can see that this left-hand side is now equal to the right-hand side. We are able to show that the left-hand side is equal to the right-hand side. I hope you learned something from this video. See you again next time.